Grazie. Thank you. Okay, I'll use the analogic pointer. Thank you. It's a pleasure to be here after 5 years when I've been to the GGI school, this one, but I'm sure that you can recognize many faces here of young postdoc now. And yeah, so it's very nice to be back to the GGI. And I'm gonna talk today about flavor jets. What do we mean by flavor jet? Well, you know that mainly we talk about jets, which can be considered as a proxy for B or C quark in the R scattering. So you have like this EV quark in the R scattering process that they fragment into hadrons, like B or D hadrons. And these B or D hadrons are, let's say, containing some anti-KT jet, and so we call this jet as a flavor jet. And so we are really interested in this kind of object in order to study this process that featured this quark in the R scattering. And why are we interested in process with flavor jet? Well, this is just an example. The example is, for instance, if you study W plus C jet, well, this is a leading order diagram. You see clearly that by studying this process, we can directly probe the strange quark PDF. And indeed, if we include, for instance, Atlas CMS data for this process, we improve of the strange PDF. But not only for the study of the proton structure, but flavor jets are also important for Higgs, new physics searches, and top sectors. So they're really important if you want to pinpoint a specific scattering process and at the same time reject the background. So, okay, naively, we all understand what we mean by flavor jet, but how are these jets precisely defined? The usual experimental definition of flavor jet is the following one. So basically, you take an anti-KT jet, and then we declare its flavor if it contains at least one EV hadron with some PT greater than some PT cut and within some distance from the jet axis. So this is usually the definition which is dropped as a true label in Monte Carlo samples, but actually what the experiments do, they train this sample, they use this sample to train some machine learning architecture, which they are usually referred to as high-level taggers. And then at the end, what they actually use when they use these taggers are low-level variables, such as, I don't know, the impact parameter, the position of the secondary vertex, and so on. But what matters to us is exactly what is the definition that they use at the truth level. So if we study carefully this definition, we realize that this definition is both soft and collinear unsafe if we want to perform massless perturbative QCT calculation. What does it mean? This means that arbitrary soft and or collinear emission can alter the flavor of the jet. And this is something that from a theory point of view, we don't like. I want to remark the fact that it's really important to have an infrared safe definition because, for instance, if we forget a moment about flavor, but consider standard jet definition, is actually, I mean, at the beginning of, well, like 20 years ago, when people started to study new generation of algorithms, it was precisely the motivation to get infrared safe algorithm that led to amazing progress in the field. Starting from, I mean, this progress triggered work on jet era, pileup subtraction, and paved the way to jet structure. So, I mean, it's really important to also, let's say, solve this issue with flavor jet in order to advance in the field. And let me scrutinize a bit the experimental definition. So the first issue is when we require at least one EV hadron, because we have this problem. The problem when you have a gluon, we split in a QQ bar. Well, this thing is always flavor, even in the collinear limit. But this can simply solve by imposing an even tag veto in the calculation. So if we apply this simple patch, we solve the issue. The other problem is with the PT cut. Well, here the problem is due to the fact that you can have a flavor quark then split into a collinear gluon, and basically, if the glue is hard enough, this falls below the PT cut, and so we get a flavorless object out of a flavored one. So this, with the PT cut, it requires a fragmentation function, but if we remove the PT cut, basically any infrared safe flavor agnostic algorithm with, at the end, recombine the QG pair. So these two problems, we can solve them in some way. The real problem is this one. The real problem is due to soft large angle G to BB bar pairs. For instance, you have a gluon, which split in a flavor quark pair, and then one quark goes inside the jet. So this is the typical configuration of non-global logs, and this is exactly what spoils the infrared safety of the algorithm. And there is no way of fixing this issue within a flavor agnostic jet algorithms. So these are the issue, and how can we solve them? The first solution has been proposed almost 20 years ago by means of the flavor KT algorithms. Basically, you modify the distance, so you start from the usual KT for jet algorithms. You modify it in such a way now it becomes flavor aware. So there is a different distance whether the particle are flavor or not. And this is okay, but the problem is that if we use exactly this prescription, we get jets which have a different kinematics. They are not anti-KT jets, and so it's not so straightforward this definition in the context of LHC. And so if here is a prediction for Z plus B jet, this one is for W plus C jet, and they both adopt flavor KT, but it's not so straightforward, the comparison to experimental data. So motivated by this thing, in the last year, there has been a lot of proposals. Also, Simone briefly mentioned them yesterday, in a way to solve the limitation of flavor. Briefly discuss them now. So let's start with the first two. The first two are proposed by this group of Simone and collaborators. So basically, the idea here is to in such a way, as I told you before, the problem is due to large angle soft QQ bar pair. And so one say, okay, I can use soft drop, which is a well-known jet structure tool, which allow you to remove soft radiation from the jet. So the idea is I use this soft drop to remove soft quarks. And then from some technical reason, I should use this JADE algorithm as a recluster. In this way, I managed to solve this issue at NNLO, but the issue appear one order higher. And so basically, this solution is known to fail at this order. There is another interesting approach, the one of defining the flavor of a jet as the flavor of the particle lying along this particular axis. This is interesting from a theory point of view, but it's called linear unsafe. So you need some specific fragmentation function. Then there has been a proposal by Chacon, Poncelet. They basically take the anti-KT and they slightly modify it. They use this is the standard anti-KT distance. They introduce this S factor, and basically the S factor is also flavor aware. And basically, when I and J are of opposite flavor, they adopt this factor here. And the idea is exactly the one of when you have soft QQ bar pair, you tend to, in this way, you recombine them before recombining the quark with any other partner in the event. So this is the main idea. It depends only on this parameter A. And basically, when A goes to 0, you recover exactly the anti-KT, but of course, you are not safe from the point of view of flavor. So they propose to use a value of A of 0.1, and they do some study, and there is there is some dependence on this value of A. So one should be careful to use the proper value of A in order to be infrared safe, but at the same time not too far from the anti-KT kinematics. Then there has been a proposal by let's say Oxford MIT group, and their proposal is basically the following: they don't use directly anti-KT distance. Well, they use anti-KT distance, but they do things in an interleave way, in the sense they use anti-KT, and then at any point of the clustering, they check whether there is some problematic configuration they have to take care of. And this is defined by means of this neutralization distance. We tell you whether there are some particles which should be recombined before going on. And if this is the case, basically you neutralize the flavor in such a way you are not infrared unsafe, and then you go on with the anti-KT distance. So it's really both the usage of anti-KT and the same time of this neutralization distance. And they show that they reached exactly anti-KT kinematics, but at the same time being infrared safe with respect to flavor. Always, yes. They have basically this parameter A, and then there are other, the power here, P, Q. So there are 3 parameters, but I mean, for any value, they always reach the anti-KT kinematics. Okay, and then there is our proposal with Rory Gold and Alexander Haas. Basically, our idea is we start from jet already cluster. So we start from anti-KT jets. And based on the flavor information of the events, we try to determine the flavor of the jet in an infrared safe way. So basically, the idea is to, I mean, this is the first formulation of the algorithm. Later will be clear there will be a second formulation. So I want to give many details here because we have revised this version. But the idea is exactly to try to get some flavor input in the events. And then at the end, we basically run a flavor KT clustering algorithms by using directly jets and the flavor particle. And in this way, we should be infrared safe with respect to flavor, and at the same time we have anti-KT kinematics by construction. So we are by definition. Okay, so as Simone mentioned, the jet flavor has been a hot topic in Les Houches. There have been many studies started in Les Houches. We need, of course, to go on with these studies, but I mean it's really a hot topic now. And we have also in Les Houches created this repository when you can find the fastest implementation of the algorithm I presented. This IFN is the flavor neutralization, then the Softrop one, the second meat of Poncelet one, and our flavor dressing. So you can find the implementation there. Okay, I will just open now a parenthesis about some application of flavor dressing, which is not really related to the main topic of the talk, but I guess it could be of interest from many of you. So I directly moved to this one because this is really the first application we studied, which is Z+C jet at LHC. Because I mean, this is really a process which allows us to study the presence of the charm in the proton, and in particular the presence of the intrinsic charm in the proton, given to the LHCb kinematics, we are really probing high X here, so we're really probing the so-called intrinsic charm component in the proton. And LHCb has measured data for this ratio when you basically consider the rapidity distribution of the Z, and you take the ratio between events of Z+C over, let's say, the flavorless Z+ jet. And we exploited the property that now, thanks to our new algorithm, we have flavored jet with exact anti-KT kinematics at the numerator. So, I mean, we can take the ratio in a faithful way. These are the LHCb fiduciary cuts. And I want to point out particular this one, because I mean, we are really working in the forward region. So we basically explore, we also study the possibility of having a theory-driven cut. We explore this possibility of having the cut is defined in such a way the PT of the Z+ jet system is less than the PT of the jet. And this is due to the fact that we want to limit this configuration here, when we observe a Z+C, but the C does not come directly from the proton, let's say, but come from some radiation out of some hard flavorless quark. So we want to limit these cases. And so we basically, so this is at Bohr level exactly 0. And so at higher order, the cut limits the RQCD radiation in a dynamical way. And okay, we do not compare with LHCb data for 2 reasons. First, because the definition they adopt in the experiment is not infrared safe, as discussed before. And second, because we found a significant contamination from MPI in this forward region. So here we plot basically what we get if we turn on or off MPI in an LO plus PS simulation, and we see that indeed there is an effect which can be up to 10%, and is also rapidity dependent. So we refrain from making a comparison from these two reasons. But in any case, if we try to study some observable, what we see is that basically we get a nice agreement between the NNLO and NLO plus PS result, both with by using Pizia and Ervig as showers. This is nice, but at the same time, the NNLO lies within the two results, but has a smaller uncertainty band, and this is true for many distribution. And we can also observe, so the difference between the right and the left is the presence of this additional cut, theory-driven cut, and we see that this cut seems to improve the perturbative convergence. So in some way, it's limiting this problematic configuration I discussed before. This is the PT of the CJET, but we also have the YZ and the ratio, what has been measured by LACB. But for all the observable, the same comments apply. Okay, so now I close the parentheses, and I go on with the general topic of flavor. Sure, yes. Yeah.
Since you ran the Monte Carlo, did you check the difference between anti-KT CJETs and flavor KT?
No, we didn't. It was a good question, but we didn't. Okay, so how to test infrared safety? So we said, okay, we declare our algorithm as infrared safe, but how to really test if they're infrared safe or not? One first test we can do is some test, let's say a fixed order, in the sense that one can take, for instance, the ±2 jet, and you start for, let's say, a Born level when you have a pair of flavored quark. So what you should see is that in the presence of only soft or collinear radiation, as measured by some event shape, you basically always should recover the two flavor jet when this observable goes to 0, because you start from Born, which is flavor. And what you see, so if we start from order alpha S, when in this case you just have an additional gluon, so any algorithm is safe, because you cannot have any additional flavor emission. The problem starts to appear at order alpha S square, and we see that the flavor dressing here in blue seems to be safe. Whereas if you take, let's say, a naive KT algorithm, we see that indeed we do not go to 0 as we probe the infrared region. And we have to also test the one order higher, alpha S cube, and in this case you see that the flavor dressing is still safe, whereas let's say the naive approach is still is unsafer at this order. So these are nice tests. These are, however, at fixed order, and so we can ask ourselves how to probe to all order the infrared safety. This is not at all a trivial question, because I mean flavor has a lot of subtleties that can appear at arbitrary higher order. And people in this paper, this is the paper by the Oxford MIT group, they basically develop a numerical framework in order to test infrared safety, let's say at all order, potentially, in the sense they start with a set of R jet depicted in blue, and they add an arbitrary number of infrared and collinear emission in the initial and the final state, and then they check whether, let's say, the flavor jet that they reconstruct in this event are the same as the flavor jet they reconstruct in the dressed event. And if this is not the case, then you have an infrared safety issue. And this numerical frame is pretty powerful and has allowed them to discover some issue both in the CMP algorithm, but also in our algorithm. And that start to appear at higher order. So let me precise that this is the relative order with respect to the Born, but alpha square mean that on top of the Born, and in our case, the issues start to appear when you have R particle, and then you add 2 additional emission on top of those. So this is a configuration that should appear in the Z plus BB bar at M4LO. So I mean, it's really higher order, but I mean, it's there, and so we should treat them in some way. And the problem is precisely due to the fact that basically in our first version of the algorithm, we had 2 stages. And in the first stage, we basically combine flavor particle with collinear radiation, flavorless collinear radiation. And then in a second stage, we were using this object as input to the second stage. But this is a problem because there is this case when you should not do that, in the sense that you should really recombine, for instance, this Q prime bar, Q all together in the first step, because if you recombine, I mean, there could be an ambiguity whether you combine this with this, with this, with this, or this with this, and this creates some issue in our algorithm. Instead, for CMP, there was an issue with the angular distance, but they managed to find a fix in the sense that you replace this angular distance, this S distance with this angular factor, which is the one defined. Well, it's not exactly the same, but is related to this neutralization distance. So you have to tune, opportunely, the soft factor. But if you adjust that, it seems to be safe. Okay. As for our algorithm, we should have found a fix in the sense that if we avoid flavor cluster, but we directly apply the flavor KT distance between anti-KT jets and all the particle in the bands, both flavor and non-flavor, this simple fix seems to be enough to solve the issue. And so here is a plot where basically at order alpha square cube 4, 5, 6, you see that as we go in the infrared region, basically the fraction of fail-leaving events seems to go to 0. And we should thank the author of this paper because they made the framework available to us so we could do our own test. And so we are working in fixing the algorithm, but these results seems to be good, and so seems that we found a solution, and so in principle also this algorithm has been fixed. Okay, so this is my final slide. So given that now we have a lot of recent proposal about the definition of flavor jet, and we managed to find the good anti-KT infrared safe jet flavor definitions. This basically is good, and we are comparing them. We started in Les Houches, but we are going on now with this kind of studies. And we should ask ourselves how feasible now is the experimental realization, because if we say we agree on an algorithm that the community should use, but then if the experiment cannot directly use it, then it's completely useless. So the purpose here is to find something that is good both for theory and experiments. And yeah, that's it. Thank you a lot for the attention.
Much for this interesting talk. More questions?
If you go back at the slide where you showed the Z plus the C jet, I have a curiosity. So
which one?
I think one before. Right, when you basically evaluated this ratio.
Yes.
So as far as I understand, but correct me if I'm wrong, you basically you produce your event, which are Z plus Z event with anti-KT, and then you run your flavor algorithm to identify which one are the flavored jet.
Yes.
But I mean, my question is, does this requires either you have some sort of n tuples for this fixed calculation, or to redo the calculation from scratch, or is there something that I'm not understanding?
So we are not storing the events when we did that, but on runtime, basically, so you evaluate everything on runtime.
But this requires 2 runs, one for the numerator and one for the denominator.
No, we just run the denominator just for flavorless. Of course, you need a lot of events, because then you want to also use it for Z plus C.
You do histograms, okay, yes. And then you take the okay. So, but then you can do it with
because if you generate directly Z plus C, then you're biased in some way, no?
Okay.
Because we don't want only the C from the art scattering, we want also the C from the shower, let's say.
But in principle, there is the advantage that with one run you can change, you can do multiple flavor assignment and study them at the same time.
Sure.
Okay.
Yeah, sure.
Okay.
Yeah.
Thanks.
Right. So you said you didn't compare to data because the algorithm that the experimentalists use is obviously NTKT, and it's infrared unsafe. But then at the end, you also said that sort of unless the experimentalists use any of these, they're useless. But I mean, in reality, quarks are massive, right? So in principle, you have none of the issues you presented, and also you're already all orders, right? There is no thing, and all of this to me seems to be only for massless calculations. So
I fully agree. I had a slide on that, but I removed it, so I'm sure we should have kept it. So the idea is, first of all, very obvious comment is say, okay, for many processes now we have only massless calculation. So if you want to compare now, you have to do something, or otherwise you wait some year and then you have the massive one and then you use NTKT. And the second answer is that okay, it may be that okay, so if you have an infrared safe definition, you potentially have log of the mass. In this way, you don't get them. But you could say, okay, but this log maybe is insignificant, so you don't care. And this is true. But when you have a process like Z plus CJet, when you have the C in the initial state, then you, from the first place, cannot do the calculation if you have the C massive, in the sense that you need some way to resum the logarithm in the initial state, which of the by Diglab. And so, yeah, but I fully agree that for process when you don't have, let's say, massive quark in the initial state, and you have the massive calculation, then use NTKT. So it's yeah, the important thing, I guess, is having the exactly same similarity. Yeah.
Right, you should be able to, at least to compare with them. So there shouldn't be any issue in comparing to data, even if they use NTKT.
No, you can compare, but if you define the flavor of jet in a different way, you're...
No, the flavor assignment of the experimentalist is a procedure, right?
Yeah, also our
algorithm A, B, C. I mean,
but no, right? In this case, it doesn't.
No, it does.
The kinematics is the same, but what you I also realized this only recently. The way you decide whether event jet is C or not is an algorithmical procedure which varies, right? Then a big okay.
No, before I don't present it, they know that they agree on what is the feature.
But they're all different, right? And this is fine. But if the end point is that I want to recover NTKT jets, I understand this flavor thing, but I don't see how can this change. I mean, how can it be different from the experimentalist point of view?
No, it's the same.
Whether they use NTKT or your algorithm, they should get the same jets.
Yeah, the experimenters need to know, also need to say which one is a CJet or not. And the point is exactly whether they can apply the same, because they could not apply the whole procedure by...
But what I'm saying is that for experimentalists, it doesn't matter.
I mean, it's not that it doesn't matter, it's that they could have different definition of what the CJet is, so they don't care because all their data have they don't have divergences, they don't have safe, but they have to choose a way to define what is a CJet or not. And we theorists will be able to calculate to give our prediction within the same definition, which this didn't work as far as I understand from the
experimentalists are certainly measuring something, but there is no status prediction for so when they compare, we don't know what to say. Oh, yeah, it's nice.
Just to second what he was saying before, I mean, I think for bottom, it's a bit more solid. Okay, because for the charm, I fully understand that. I mean, it's what is massive prediction. Then you don't have the charm in the initial state. For the bottom, is a bit more. I mean, I would be careful to say that the algorithms are unsafe because, I mean, the algorithm is safe. As long as you keep the bottom massive, it's safe. The bottom is 4.5 GeV. Of course, if you look at PT of hundreds of GV, then it's a problem. Then you will have the logs and all that.
I fully agree with what Massimiliano said.
Actually, I am slightly puzzled by what Massimiliano says, but it's not what I wanted to ask you, in the sense that the mass will protect you from collinear problems, but the mass of a quark will not protect you from a soft problem, and it's not completely clear to me that at some order, the soft problem, the radiation of a soft gluon from the massive quark will not downstream generate something that would affect the definition. But as I said, maybe you want to say something.
No, but I mean, if you keep the mass,
a massive fermion emits gluons that are still divergent.
Sure, but then the problem is always when a gluon split into a QQ bar.
Yes,
no?
I can see that. So at the first order, I understand it's okay. Whether, you know, at some downstream, some further radiation will not do damage, I'm not so sure. That's all I'm saying. However, I have something which is completely naive,
okay,
that I wanted to ask you. At least one algorithm, not yours, but possibly also Gavin's, they have a parameter that when you send it to 0, you recover anti-KT.
Yeah,
which is not infrared safe. And this makes me feel a bit strange, because I always thought of infrared safety as a discrete thing, sort of like being pregnant, right? That I have a hard time imagining a continuous parameter that you are never pregnant, but in a certain limit you are. So could you clarify how does it work? I mean, how is it possible that I have a number that I drive it to a certain value and all of a sudden, crack, the thing falls apart?
So with this flavor neutralization, I'm not so sure that there is a parameter that you can send to 0 and you recover anti-KT.
Here also I was not sure, but the other one also.
The other one, for sure, the Chacon one, yes.
Yeah.
This A, when you send to 0 is anti-KT.
Yeah.
Because basically in that case you get, well, this the S become 1, no? And so you get exactly the anti-KT.
This is now.
If you take the angularities, the Sturman's angularities, they are safe for values. I mean, angularities, they measure Z times angle to some power. If that power is less than 0, then it's unsafe.
It's the power.
Ah, okay. Well, you take the log, the power becomes.
Well, there's time to discuss over coffee. I understand we have a coffee break, even though we are not coming back after the break here. We convene tomorrow morning at 11:15 again.
Thank you.
Thank you.
Thank you.